describe it, some objects or some materials, we can describe it to be elastic. Some materials we can describe to be inelastic. بعض منها it's called elastic مرن, بعض منها اختلاف غير مرن. Now I want to say something in the other way. What is actually the elastic? Elastic doesn't mean that it can bend easily. No, that's not elastic. Elastic is a material. If you apply a force in it and remove that force, it will retain its original shape. Again, it's a material that is. If you apply a force in it, deform it, change its shape, and remove that force, what happened to the material? It goes back. It restores its original shape. It retains its original. This is called elastic. I need to tell you something. From iron as an example, here, we can consider two things. We can consider the iron rod, قضيب من الحديد, and we can consider the spring. By the way, both they are made of iron. And we can say this is inelastic, because if you actually deform it by applying a force, it will not return back. And this is elastic. Oh, you can say, okay, whether they have different material, no, they have the same material, but they have different shape. They behave in different ways. You got the point? So that doesn't mean, when we say elastic, the material is always, we can say the material is elastic. I don't mean that always iron is elastic. We can say sometimes it's elastic, sometimes it's inelastic. Okay? All other materials you can measure in the same way. Now let me show you something. This is of course the lecture. First of all, if we talk about something inelastic, just this is golf ball and this is golf bat. If they simply you hit the ball by using the bat, you know the ball simply is inelastic. It will not deform. The whole actually power or force applied by the bat will transfer to the ball, and the ball will shift or move from according to that. Now this type of ball, which is here very hard, we call it by rigid. You know the word rigid, صلب يا شباب. Okay? This is an idea. Now, in the same thing here, we just here. Now, let me think. Sometimes يا شباب here, we have something inside the springs. I need to introduce this for you. It is called by restoring force. See, in spring, as an example, if you have a spring which is suspended to the ceiling, just like a spring, and follow me, here, we say this is position. If we do not actually touch the spring, it's called equilibrium position. وضع الاتزان يا شباب. This is equilibrium, okay? Now what happened? If you simply pull the spring downward, it will extend. راح يستطيل, صح? Now if you pull it downward, pay attention now, it will become like this. As an example, now you just pull it like this. What happened here? We call this change in linkage from here to here. We call it delta x, which stands for extension. Extension means change in length. Change in length. Okay? By the way, I'm going to give you two cases when we just simply stretch and we compress also. This is called change in length. Now, my idea is what? Pay attention, Ishmael. You pull that spring downward. We say in another word, you actually causes actually displacement downward. Inside the spring, I'm not talking about your force. Inside the spring, there will be another force generated. This force is called by restoring force. This force will actually retain the spring to its original shape again. This force, has the direction of what? Opposite to displacement. So this force I'm going to call force of spring. Pay attention, Shabab. This force is not your force. Suppose you are suspended something here. I don't care about this one. This force is actually, here is called the restoring force, which is generated inside the spring. Okay? Now, according to this, if we remove this, what happened? It will go back. Due to what? Due to this force. You figure it out, Shabab? Now, this force we call Shabab is a restoring force. So in another way, Ya Abdullah, we can say that elastic objects that the object they have a restoring force generated when we displace them. This is another thing. Again, we define that here. Elastic simply is an object. If we apply a force in it and change its shape, it will retain. In another way, an elastic, we can say they are a material or subject that they have a restoring force which will retain them to its original shape after the removal of applied force. Now, the third case, pay attention now. Suppose this is equilibrium, you just compress. What happened now? It will become like this. Is that right?
Yes.
And of course, if we assume this is the original one, I need to show you something, but it's here. So this is also, by the way, so we call it pi delta x. Change in length. Now, delta x is actually upward. Where's the restoring force now? No. This is my restoring force. And this is the way here, Shabab. This restoring force. Now, all the objects that they have restoring force, they are described to be an elastic object or elastic material. This is not only the springs, Shabab. There are some material, just like the rubbers, it's also called elastic. When you pull that arc, pull it here, arrow and bow in it, it will just, when it move it hand, what happened? The rubber will go back to its original shape. Is that right?
Yes.
There's many things that we have it in according to this. I hope so now this is what we call bielastic is clear for you. I have a question. Now I need to. If we have a steel rod and a glass rod, they are similar to each other. If we want to describe which one of them is we can say more elastic or partially elastic than the other. Barakallah fi. Why?
Because it won't break.
Glass can take the pressure.
No.
You answered. Go ahead. Do something.
Glass don't have restoring.
It will never return. When you break it simply, when you try to bend it, what happens? It will break. It will never return. In case of steel, it will bend. But then what happens? You can straighten again. يمكن ترجعوا مرة ثانية يا شباب بوضع السنة. We say, by the way, I told you, the spring is made of steel. So this is, in case, we can say it can return to its original shape. So that we have, it have a degree of elasticity more than the glass. It's not perfect elastic. By the way, there is something called perfect elastic. And this is here partial elastic. It is just like that. Okay, Shabab? Fine. They mentioned for us here, I need this one only. Restoring force is a force that restores a system to an equilibrium position again. Springs, rubber bands are basic example of elasticity. System that exhibits restoring force is called bielastic. Now, see, elasticity and restoring forces are also properties of stiff systems. I will explain this word, such as steel, glass, human bones, and twigs, trees. By the way, also, all these we can explain it in form of field. We say that steel is more elastic than glass. By the way, inside your bones, you have two types of bones, by the way.
Spongy and compact.
Yes. Is that right? This is good. And by the way, also we can say, what about the bones inside your ears? Yes, it's a cartilage, not the roof. That's why it's a kind of bones, by the way. It has more elasticity. If you just apply a force in it and retain, it will retain back. Otherwise, you have a problem. If you hit with your nose with the ball, with the wall, it will remain. Actually, it's back. That's why this is a net. Is that right? So, and twigs of trees that we know it. Okay, أغصان الأشجار يا شباب also. Now, we need to go here. Just wait. We found this about here. I think you studied this before. There's actually law. It's called by Hooke's law. Hooke's law simply studied the relationship between this force of spring and displacement. And this is indeed, you can know that. This is a linear relationship. How? If you have here a spring, see, so this is the equilibrium. If you pull it a little bit, it will expand up to here. If you add 5 Newton. If you add 10 Newton, what happens? To expand more. Is that right?
Yes.
10 Newton. If you add, for example, 20 Newton, it will add more and more. You agree about this?
Yeah.
And this is logic. So what we say, more active load, it will be more extension or displacement. Is that right? So this is in the same manner, we say that the relationship between the force and here, force and here, we have the extension or the change in length. It's a linear relationship, a straight line. If this increases, this will also increase. You got the point? Now, we want to write it in letters. We say, Shabab, simply, force of the spring is directly proportional to the delta x. Now, force of spring, we will remove this proportion sign. We put something constant. We did this before with you. Always be times delta x. This constant, it is found to be k. And k is called the spring constant or stiffness constant. Stiffness means معامل الصلابة. So this is F of spring is equal simply k times delta x. Now, this is the force, what we call by the restoring force generated inside the spring. And this is the change in the length of the spring. Now, this is constant, depends on the spring. And this constant, first of all, has a dimension of a Newton per meter. Is that okay for you? Because k is equal to F over
Delta.
first of all. Now, I want to say something. More the value of k, Shabab, here, stiffer is the object. And less value of k, actually softer is the object. Stiffer يعني أصلب, softer بيكون إيش؟ أطرى. Okay, Shabab, this is it. So as here we can say, more k value, this is constant. We call the object is stiffer. Stiffer is أصلب. And this value, we call by it is softer. Okay? Now, every spring has its actually specific value of k. Let me give you an example. We have springs, for example, used in cars, and the same springs in shock absorber. You know that. And the same spring we use it in trucks, Yaqub. Can we say this, the springs used in truck is the same as we use in the car? No. Now these trucks, they are actually designed to have a loads, everything. Not just like the car. So that we have different k value. We have also different k value. Everywhere we have springs, they have their own origin. That's why I want to say something. Please pay attention. In any problem, ya Shabab, if you find the value of k, you consider it always available. You can use it anywhere for the same spring. Why? Because it's constant for the same spring. So if you can't find it, you can apply it to any other problems or any part of the problem. Always we consider k as just like g for gravity. Always you apply g for 10, is that right? You just the same way. If you have anything, you have springs, Abdullah, you have rubber bands, you have plastic, you have anything, if you find the k, you consider you have something constant related to that material. You can apply it anytime for any part of the question. طيب. This Latin is simple. This is equilibrium now. You just compress. This is the displacement. What happened to the spring is opposite. We simply stretch the same thing. This is the displacement and this is here. Now, I need this one low. I need to give something more, we can say, sophisticated here. F of spring, I will write minus k times delta x. Who can tell me why I put the minus sign? Yes?
Because k has the opposite direction of delta x.
Not k. Because force of spring, k is constant. It has a different direction, opposite direction of displacement. See it? We have delta x and we have force. We don't have k. K is something inside the spring. Okay, Shabab? So this is that rule. But by the way, Shabab, we're not using this actually in problems. In problems, you can consider what? Absolute value of it. This only negative sign shows that the displacement and force, restoring force, they are always opposite. Only to show that. Okay? Let me show you now. We have this one, Shabab, here, according to that. You see the same question. I will read this for you. The negative sign says that restoring force and displacement are in opposite direction. Please just here put me. Now, I want to say something also. The spring constant K is a property that characterizes here a spring, just as the mass characterizes a particle. Large K means that large forces need to cause a significant stretch, and the spring is called by is a stiff spring. By the way, K is not using always for spring, Yeshiva. You can use for any elastic material. That's why I prefer to call it as a stiffness constant, not a spring constant. This is sometimes confusing for them. بعض الطلاب يقول لك K is only for springs. No. Sometimes if you have that bow and arrows, there is a K also for it. Did you know sometimes we have a lot. In these, sometimes you can use a very stiff one, so the charge you cannot simply pull it backward. This happens. في سلاح دائما معروف جدا هذا بسيط. هذا سلاح تتركه بيد الطفل. هو نشابش بيكون اسهم صغيره وفي ايش؟ سلك حديد يعني مرن برجع لورا. هذا مستحيل الطفل يرجع السلك، لازم واحد ايش؟ زي المسدس. طبعا بعطيكم الفكره، المسدس فيه امان. ليش؟ عشان الأمان هذا مستحيل الطفل يفتحه. حتى لو تركت المسدس مع الطفل اتس اوكي. إنه هذا لازم إنه يفتح الأمان وهو بيكون قوي. يحتاج واحد قوي حتى إيش؟ to open. This is the same thing here. So put this in mind. K is not only for springs. K for every elastic material. Is that right? طيب we talk about the stiff and soft. Fine. Let's go to this question. I will raise this for you. Here. A scale used to weigh fish consists of a spring hung from a support. The spring equilibrium length is 10 centimeter. When I say equilibrium length, that this is I can consider this is my X1 equilibrium without stretching now. Do make sure, when a 4 kilogram fish is suspended from the end of the spring, just like this one, it stretches to a length of 12.4. How much is your delta X now? 2.4. Now, this is X2, so you can say delta X simply. You can calculate it's X2 minus, so it is 2.4 centimeter. Is that clear? Yeah. Now, what is the spring constant for this spring? When we write it simply, F spring is equal to K delta X. I can write that K is equal to F of spring times, I know, for example, delta X. How much force of spring?
9.2.
Yeah. Okay, why? This force of spring is here. And see, here, what causing this force is actually the weight of fish, which is, by the way, 40 Newton, because it's 4 kilogram, okay? Now we say, this is an equilibrium. The fish is not moving up or down, stop down. When they actually stop at equilibrium, we say that this force should equal this force. This is something actually comparison. We compare it. You got the point, Shabab? So precisely, we put this here. Simply, you just write it mg over delta x. So you say 40 over 0.024. Is that clear why 0.024? You have to convert to meter. Okay, is that okay? Now we find the value of K. By the way, we write a lot of details here. I need this one here, just only. Now we found that K is equal to 1600 in Newton per meter. I'm sorry, but here, I'm not going to stick with these signs. We try to make it simple. Sometimes the sign is important, sometimes there's no. There's a lot of, actually, we can say words and signs. No, we know that this is here. They consider this is negative, this is positive, blah, blah. You know that from equilibrium, you just equate these both. Now, let's go back to the question. See, if an 8 kilogram fish is suspended from the spring, what will be the length of the spring? Who can answer directly?
4.8.
The length of the spring, Abdullah. You are close.
Oh,
It will be?
F. 14.8.
Okay, 14.8. Yes, that's it. طيب يا شباب, see, since it's linear, I told you that this relationship that we said that here, f and delta x, what is the relation? It's linear, is that right? So if this is 2, this is 5. If this is 4, this will be 10, is that right? So the same thing, see, Ishmael. We have 8, now here we have 4. In 4 kilogram, we have an extension of 2.4 centimeter. In 8 kilogram, we have extension of 4.8. So the length, the final length, of course, it will be 10 plus this one, so 14.8 centimeter. Is that clear? This is how we just do it. There's no need to just explain. They just here explain it and they continue it. I don't know why they just talking a lot on that one. Finally, how much is it? 14.8. You have any question about this? I need to emphasize on this. See here, please, don't try to stick with these negative signs. Always, I need to say something. When the object is in equilibrium, you consider that total force is equal to 0. That means, don't try to take positive and negative forces. That means upward forces should equal downward. Or right forces, that's much more easier for you. لا تعقد حالك عشان تكتب اللي فوق موجب واللي تحت سالب بعدين تنقل السالب للجهه الثانيه صح؟ يعني هذا بتكثر حالك الخطوات for nothing. You take it simply. By the way, we are not actually acting upon what is the steps that you have to follow. We need only the final answer. This is the style of your question. Your question actually all of it, what is it? Multiple choice question. صح؟ ما يهمنا تحل ان شاء الله باي طريقه، المهم طلع الجواب الصحيح. What your question? Okay. Yes sir.
ليش في معطيات الواي بالسالب؟
أنا بقول لك ليش بالواي بالسالب. Because it's going downward. في الكتاب عندكم يا شباب here. See, this is the axis. في الأكس to the right is positive, to the left it's الواي. Upward it's positive, downward it's عرفت علي؟ فالواي is always written as to be downward. You got the point? الواي تبدأ من هنا تنزل. طول 10 سم for example this is your 10 بعدين صار 15 أو 14 this is like this صح؟ So it's always negative. That's هذا يا قرني بقول أنا لا تتقيدوا فيه هذا. في الكتاب they stick with it okay but أنت you got the point. خلاص ما في داعي إنك you have لما إيش؟ أخاف إنك تحط واحدة وتنسى الثانية يطلع معك جواب خطأ. So be careful about this. طيب. Let's go to the next point. Now we have something also. See, Ishmael, how we sometimes we can model the material. We always, it's mentioned here that we model most of the material as a being made up of particle-like atoms connected by spring-like bonds. Just like sometimes, Ishmael, in the TV actually advertisement, you see what is inside the detergent. مسحيق الغسيل بيقول لك this is the fibers inside the cloth. It is just like that. Suppose. Now I have this marker. If we consider a part of it, it's made of particles, is that right? Or you can say atoms. Now these particles, they are connected by each other by just bond. These bonds in chemistry is bond. Now in physics we say just like springs. Okay, just like this one. Now I want to say something. Just like these. If you simply stretch the material, now these spring they will stretch and the material will elongate, it will become more longer. By the way, is that true? Yes. And we cannot simply, it's not significant for us. I'm going to do something for you. Now suppose this marker has a length of 10 centimeters exactly. I did this one. I just tried to stretch it. Now, for you, it's still tens. It's very hard to measure the difference, correct? If you have the proper device, إذا كان عندك الجهاز المناسب, there is a difference. But that proper device, you cannot simply signify it. Now, I want to say something. Okay. I have my hand. I put my hand on the wall. And then I can say that I have hundreds of thousands of bacteria and germs on my hand. Can you see this, Abdullah? But is that true? But there is no, it's true. By the way. It's true, yeah, that's correct. I can prove this for you. You took this in biology and other material. The idea is what we cannot simply, as a human, we have our own capabilities. عندنا قدراتنا شو, we cannot simply use. So what? By the way, these germs, bacteria, they have no access to my body because there's a skin. But if I have a cut, at that time it will be risky for me. Correct? In the same way, when you pull the object, you cannot simply, here we can say there is no significant change in length for you. But there is something inside you. Okay, if you continue doing this, just like that, sometimes you will break it. We say that the materials or these particles, they will actually separate till it will start fraction here. There is a fraction and there will be cracks between the particles. Okay? This is how we, now why we study this? These simply springs in physics, just like the bonds, ionic and covalent in chemistry. These actually describe how much the rigidity of the object. More springs, more rigid is the object. And less spring, less rigid is the object. Okay? Now, if this is clear for you, Ishabah, we can say, for example, I'm going to tell you something else. I think you took this in chemistry. In chemistry, if we have the solid particles, how we draw it? This is the solid particles. They are connected like this. You took this with the chemistry, I think. Is that right? Yes. There's a force, a large force thing. But in here, in liquid particles, there's no, actually, they are close, but there is no something between them. Here, there's nothing between them. We can say if we have this one and this one, which one is more harder? This or this? Because you have more bonds, you have to break. Is that right? So this is much more harder. This is the idea what we talk about. Now I need to show you something, Ishabah. See. We try sometimes here, when we explain something, we try simply here to figure it out from actually physical view, not from chemistry or biological view. Pay attention. Suppose we have a steel rod like this one. And you pull it, the steel rod. I can say that the force here is directly proportional to simply to the length. The force here that you apply. That means, see Shabbat, that restoring force, we can say it's more, actually will be in a long rods than the shorter long. So let me give you some. If you have two sticks of the same material, one is short and one is long, which one actually will bend easily? The longer one. It will be sometimes bend by itself. You got the point? So it actually bend easily. That the shorter one will be hard for you. Now, just like this marker, as an example, you can try to bend this marker. It's easier than bend that cap of the marker. It's shorter one. You got the point. Now, also one more point. We found that the restoring force also is inverse proportional to the area of the rod, the cross-section area, مساحة المقطع. That means, if you have a thin rod and a thicker one, the force of bending this one will be easy, but the thicker one will be hard. Is that right? إذا أعطيتك أنا قضيبين، واحد رفيع وواحد سميك. Which one you can bend easily? صح يا شباب؟ I'm talking sometimes because I need you to convince yourself first. اقنع نفسك عشان احنا بنعتمد على انك تفهم هذه الامور. So the shorter one we can say is actually, we can say the shorter here, the shorter one is more actually stiff, and here the thicker one is also more stiff. Or in another way, we can say يا شباب the longer one is more elastic and the thinner one is more elastic. I'm going to define this both. See, this we call pi, this is more elastic because it can bend easily. This is we call pi here stiffer. Now in the other one, if we have a shorter one and a longer one like this one, we say this one is more stiffer and this one is also elastic. Is that okay for you?
Yes.
Why we say this is stiffer? Because it's hard to bend. القصير صعب جدا انك تثنيه. Now why this is here is stiffer? Because السميك كمان صعب انك بالعكس. طيب, let's combine these two together. I need to introduce something for you, شباب. We have F is direct proportional to L, sorry, change in length over A. Okay? I'm gonna see here, I will remove this sign. So we make, no, I'm gonna write here, instead of F, I will write K delta X, or make it delta L, is equal, or direct proportion to, I made a mistake here, make it L, this one. L over A. Okay, Shabab? Just here simple. Now I will rearrange this. Just follow with me, Shabab. I will rearrange this how we, I will send this to the other side and bring here A. So I'm gonna say K times A is that proportional to what? L over delta L. Yeah, Shabab, here, if we exchange this now, L over delta L has a meaning. We call it by strain. And the other one is called by stress. So this is actually lead us to a formula. I'm going to show it to you. By the way, I made mistakes here, and here I will try to see it. Here I'm going to show it to you. So I made this mistake. I changed a little bit of it. Here, we assume that, where is the first one? Yeah. No. Pick up this one. I need to show you this. This is because by the stress, and this is because by the strain. Why I did it without many times. Now I'm confusing about how to get it. See, Ishbal. F over A, it's called by the stress. Stress and strain, sometimes you heard these words before. In Arabic, by the way, it has no meaning. And sometimes we use the stress in actual real life. You may ask someone, how do you like, oh, I have a lot of stress in my life these days. صح؟ يعني عندي ضغط عمل شديد أو ضغط دراسة شديد, صح? So this is here, bro. The stress is actually the force acting over area. This is a ratio. And the strength is the change in length over the original length. If you apply a force, you expect there is a change, deformation. Now, how much comparison between the force you apply and the change in length? This is the stress, and we got by the strain. Now, this is the stress and strain, and y is nothing but simply is called by Young's modulus. So you can rephrase this as a stress, CH, is equal to y times strain. The stress is equal to F over A is equal to y times delta L over L. Pay attention, Ishmael. This has the dimensions of Newton per meter squared. This has no dimension, no unit. Is that right? Yes. Because length over length. So this actually unit of y here, Young modulus is the same as a Newton per meter squared. Is that clear? Fine. We said that unit of stress is due to this, actually here stitching we call by tensile stress. This is simple. We continue this one. Also, it's mentioned that Young modulus have the same units as the stress. Stiff material has a large value of y, just like K, and soft material has a small value of y, just like K. So this is another formula. We need just only to know how to deal with this law, not more than that. If we go to the questions, you will see that we're almost done in this one. Pay attention here. I think this will be maybe the last one. Here, it is mentioned, we had a pendulum in one of the universities, just like what we call by DNA clock here in the health track campus. تعرفوا هذا السلعة الموجودة تحت. It's the same thing. Just pay attention. In the physics department, we used to prove that the Earth rotates, consists of a 120 kilogram steel pole that swings at the end of 6 meter long steel cable. This is the pole and this is the cable. It swings like this one. Now, the cable has a diameter of 2.5 millimeter. When the pole was first hung from the cable, by how much did the cable stretch? We ask for delta. Paragraph. See, and models in this one. Let us talk about the idea. See, if you want to prove that the Earth is rotating or spinning around its axis, you cannot prove it by yourself. Why? If you choose to step here and stay for 24 hours, you will rotate. But all the building will rotate with you, not only you by yourself. That's why what happened, you will never feel. Suppose this, I'm just stopping, looking to that wall. I will rotate and the wall also rotate. For me, nothing happened, change. Is that right? So, to measure actually the rotation here, that we use a pendulum. Like this one, it's suspended. And it's free to move. Now, if the Earth is moving, the pendulum is not necessary to move. It remains in its position. In this way, we can prove that the Earth is spinning or rotating, okay? Now, in any problem like this, see, write all the details that you have in question. I will write here. We have 120 kilogram. This is my mass. Okay, 6 meter long steel. What is this? 6 meter. Okay. The cable has a diameter of 2.8. So can I say the radius? How much is it? Is that right?
1.25.
Radius. Because you need something now. When the ball was first hung from the cable, how much did the cable stretch? And Young modulus is given also. This is a good question, 10 to the power 10. Okay. We need only to convert this one. Now, if we write the formula that F over A is equal to Y, delta L over A. That's everything. Now, from force, we can find from mg. Yes. Is that okay? So I'm going to write this one simply. Instead of force, I will write what? mg. Now, area, we have a cable and it has a cylindrical shape. So the area of cylinder is 2 by r. 2 by r squared. I know, by r squared. I'm sorry, that the circumference 2 by r. It's by r squared. So we have r also here. Follow me. Y is given. L is given. So what is left? Delta. Precisely. You got the point? So I think this is you need it, that the cable is just like it has a cylindrical shape. So its area is given by r squared. And force, since it's suspended like this one, we said that the force here is nothing but mg. Is that right? We took now with the fish problem, with that fish problem, we said that the force inside the spring is nothing but mg. So this is a direct, here, straightforward. And you just make the delta L here the subject and go ahead forward, okay? واضح لكم يا شباب؟
لما يطلب الفاينل ستريتش
We asked for what actually, how much did the cable stretch? He asked for delta L. لما يطلب منك الفاينل length ايوه بدك توجد الدلتا L وتضيف على ال مرة ثانية الأوريجينال. Just like what Abdullah did now, he found 14.8. He found 4.8 and he added to 10. By the way, شباب, how much did the cable stretch? He asked for delta L, not for L plus delta L, or final length. Is that clear? طيب. Now, okay. We're almost done. Only a few things that we have, and then we stop. See, Ishmael. Here beyond the elastic limit. Sometimes, Ishmael, every material has what we call by a limit or an extreme value. If you actually exceed that extreme value, what happens? It will be actually be no longer elastic. Just like what? See, if you have a spring, if you stretch the spring and then release it, it will go back. If you continue stretching more and more, it will go back. But at a certain limit, it will never go back. That limit is called by elastic limit. Just like, for example, you remember about the stability? If your actual center of gravity is above the mass. See, if you try to bend yourself, now you're stable. If your actually center of mass exceed the base, what happens? You will fall. That, what we call that angle, critical angle, if you remember. صح? The same thing here, Shabab. We have something called by the elastic limit here. If you just exceed that elastic limit, the material is no longer. السبرينج لما تعمل كده يا شباب شده أكثر من الطبيعي ما بيرجع لشكله السابق. صح؟ That means you extend or you actually exceed the elastic limit. This is here. So please, just put this in your mind here, Shabab. We have, for a rotor cable of particle material, there is an ultimate stress. Ultimate, the maximum. The ultimate stress or tensile strength is the largest stress the material can sustain before breaking. And there's also here that the tensile strength is force maximum force over area, because this is a strength or stress, F over A. Now in this one, this is here, up to here, this is called elastic. If you continue pulling it, what happens? It will break. This is called by fracture point or breaking point. Just like us يا شباب، إذا عندك أنت شيء سبرينج شديته تحول الحلقات إلى خط مستقيم. إذا استمريت في الشد إيش يصير فيه؟ ينقطع في الآخر، صح؟ This is the breaking. This is what we talk about. This simple things. طيب. Now here يا شباب, this is just give us an idea. Now this is important because it's actually biological materials. I need to show you something. يا شباب, the steel has the following graph, where its breaking point at this position, and the spider silk has this one. Who can explain this? Why the spider has more actually strain than the steel? You know, understand the strain? أكيد. ليش بيستجيب بشكل أكبر من spider? Again, I will just think of it. A graph of stress versus strain of a spider silk, and the steel shows that. If we just try to read the graph, the steel has very short, see how much the strain here? Say it's 0.01. Very good. With, say, 20 stress. Now, in case of the here, it has a large strain. So what? It's 1. You know, this is 100 times this one. And how much the strain? Stress, sorry, is 20. The idea what? Why the spider silk has more strain than the steel? Yes?
Because it's softer.
It's softer, okay.
Its ability to expand.
But from the formula, you can know that. Why it's actually still more. Yes, Emma?
Because the Young constant is like more in the spider silk than the...
By the way, Young is actually, we said it's high for stiffer.
High force.
And low for, so this is not correct. But I need to show you something. See, Ashba. Can I say F over A is direct proportional to delta L over L? صح? Without turning modulus. I need C. This is the strain. Can I say the strain is direct proportional to the force? And this is what is important. Inverse proportion to what? Did you know that, ya Shabab? Here, inverse. that the spider cell has a very, very actually small cross-section area. That means this small cross-section area, it will has, this is very small, so this value will be very high value. Again, shabab, consider like decision. Delta L over L is equal to F over A. Don't care about F. You consider this one. More area will be less strain. Less area will be more. Do you know how much actually these cells actually spider cells how they are? خيوط رفيعة جدا جدا يا شباب صح؟ This is just like webs تعمل هي شبكات منهم. These webs actually they have a very low area and hence they have a very large strain. Did you know what this means? If you apply a force it will expand. الفكرة يا شباب إنه الحديد لما تأثر عليه بقوة ممكن يكسر بسهولة الحديد أو يحتاج يعني خلينا نقول إيش يوقف عند حد معين. لو كنا عندك شبكة العنكبوت هذه السباين راح إيش تلقي فيها نفسك راح تلاقي إيش يصير تنزل فيها بزيادة كثير. ولهذا السبب it's used for hunting. هذا ربنا خلقها كذا إنه الحيوانات حتى الحيوانات أكبر من السبايدر أحيانا it will actually simply stuck with that web. Is that right? So what is it has ability to simply move in it. This is an idea just here and a case. طيب just give me 2 or 3 minutes يا شباب. Now Abdullah he just talked something about these bones. Pay attention. See it. Our bones has the following construction. I'm talking about the general bones. We have most bones in your body made of 2 different kinds of bony material. Dense and rigid cortical material on the outside and porous flexible cancellous here or spongy bone in the inside. I need to say something. Your bones has 2 actual layers. The outer layer, this one, and this inside. Now why the inside we assume it is spongy? Because, okay, he tried to link it. Yes, you understood this. Why the bones of the birds, all the birds, is spongy. You can easily break the birds' bones. لما تاكل الدجاجة تكسرها بسهولة، صح؟ Why? To make it light and fly. Now, as we follow, if you have your bones in your body and all your bones is rigid, you will be actually very heavy to move. You have a heart, and heart should push the blood in your body. Is that right? If you're heavy, مثلا أوزان من الناس كلها فوق 150 و 200 كيلو it will be very heavy for you to move, and you will never live for a long time. That's why Allah subhanahu wa ta'ala, He created the bones from outside is rigid, but from inside is spongy, just like this one to make it us little bit lighter. نكون احنا أخف يا شباب. وهذا عظمه لما ينكسر من الخارج قوي جدا لكن من الداخل بيكون ايش؟ spongy. طيب see يا شباب according to this consequently the last properties bones can be modeled as of these 2 hollow cylinders. See يا شباب. This is also if you care why it's actually according to the elasticity. From outside give me rigid, from inside it's a little bit elastic. So you can sometimes bend the bones. بعض الطلاب تلاقيه بيمسك أصابعه ويرجعها لورا هنا. صح؟ This flexibility or elastic here, elastic is sometimes in some people. أحيانا يا شباب you can measure some people or you can see some people they can fold themselves in a box. تلاقيه بيصفط نفسه داخل صندوق صغير. This is elasticity. Okay? We have. But this is in the structure of a human being. The outer bones is strong, but the inner one is light. And the inner one gives us the flexibility to bend. You have a degree of bend actually. You can bend a little bit. احنا كلنا نشوف ممكن احنا ايش؟ تسوي حاجة تنثني بسهولة، لكن لحد معين لو تجاوزت هذا الحد ممكن تأذي نفسك. This is an idea. طيب here this is the last point I think. This is summary all of it is a summary. You just go through it. الله يعطيك العافية.